Assalamu alaikum, my name is Khalid Ifzarin, and this presentation is about kernel-based regularization and linear system of identification. My reference is an article published by Leonard LeJong and his team. So this presentation shows some contribution of machine learning to system identification and control system. Those are the outlines of my presentation. System identification is about estimate a model of dynamical system from input-output data. The traditional approach was to use some statistical method for estimation, like prediction error method or maximum likelihood, and also using some method like AIC or BIC or cross-validation for model selection. But less than 12 years ago, an alternative approach called kernel-based identification. And this presentation is about to show the main idea and the result of this approach. If we take this linear system for a static system, and ET represent white noise, and with mean zero, and covariance matrix is sigma square times identity, and we write this equation in vector and matrix form, then the goal is to estimate data by making this cost or loss function small as possible. And this is the least square problem. And the solution for this problem here, it's called normal equation, and it's right as phi transpose phi inverse times phi transpose y. Now, if we add a regularization term, this term here to our estimation problem, then this gamma here is just a positive number that tells us how much weight we would like to put in this penalty term, and P is a matrix called regularization matrix, and the solution it's gonna look like this form, a little bit different than normal equation. And here it's this two expressions the same. Those matrices, they have different the identity have different size. So we're gonna show some Bayesian interpretation of this regularization. To do that, we need to use this formula for the conditional distribution of Gaussian. So if we take X and we make partition of X as two vectors X1 and X2, this is joint distribution of X1, X2, and the conditional distribution is also going to be Gaussian with the mean mu and covariance matrix sigma given with this formula. So we're going to use this formula in the next couple slides. So now if we treat this data from this linear regression as a random variable, let's say it's Gaussian with the mean 0 and covariance pi, so we put in some prior information and data. Then the joint distribution of theta and y is going to be this way, and this is the covariance matrix for y, because y is from the linear equation it's just combination of linear Gaussian, so it should be Gaussian. So using the formula we just before, then the posterior distribution of theta given y is going to be normal Gaussian, and with the mean is theta hat given with this formula, and the covariance is given with this form. And if we look to this the mean of posterior, we can compare with the estimation from regularization. We can see they're same if we take pi and replace it by p, and then we replace sigma squared by a gamma. So the empirical bias now is if we take this regularization matrix and actually we make it depend some hyperparameter eta. So now this covariance matrix of y is going to become this way because it's going to depend this p matrix dependent theta. So we call this covariance as z eta. And the goal here, the empirical bias, is about maximizing the marginal likelihood. And this is the marginal likelihood. We have to maximize this one to estimate eta. So maximizing the marginal likelihood is same as minimization of log. Actually, minimization the negative log that way. So it should be negative log, and we get this. This problem is going to become this way. So now an example for a regularization and dynamical system. If we take an example of finite impulse response, and we call the FIR, and this is the form of the equation of FIR. So GI here, this G here is some transfer function, and this GI is some coefficient of impulse response, and U is the input, and E is white noise. So if we put this those coefficients of the impulse response in vector, and we put those inputs here in vector, then we can have a linear regression in this form. So what we're going to do is to build a matrix P, that regularization matrix, that's reflect some properties of those impulse response, like to be stable and decay exponentially, and also to be smooth neighbor of those coefficients, and that's mean the correlation should be positive. So the choices we can use for this model, we can use those matrices here with the entries I and G. So this one is called DC kernel, diagonal correlated, and given in this form. And this hyperparameter eta is dependent on 3 parameters, and this rho control the correlation, and this lambda control the size, and beta is between 0 and 1. For this one, a TC kernel, it's tuned correlation. Correlated, and this is a special case for the first one. If we take a rho equal to square root of theta, beta, and then we combine those exponents. The third one is we're going to talk about when we talk about function estimation, and it's given in this form. The entries ij is given in this form, and this is a special case with order 2, and it's called cubic stable spline. So now I would like to see this in practice, how this regularization can help for this system. If we take this system here, this impulse response, and this is the true function, it came from this transfer function G, and we're trying to estimate. So we're going to use this model of IR to estimate this impulse response. So the first, what we do, we use some input U. The signal U is given in this picture, and with the variance with 1, and we take the output, and we are trying to corrupt the output with variance 0.025, and this is the signal of Y, and then we do just the all the way, and we get this estimation, this gray curve, and we can see it's not doing a good job to do a good estimation, but this is the best we can get with the order 12 using cross validation. This is the best estimation we can get. Now, if we take this, we use this matrix P, and now we're going to use just as identity, and just like regression. Then with the brown color here, the curve looks like it's doing a better job, but the problem here is not following the behavior of the impulse response. It's not stable. So that's still here is not good approximation or estimation of this function. So the last curve here in the blue, we can see is doing a good job for estimating the impulse response. And this one, it came from this matrix that we use, that DC kernel, and with the order of the model of 50, and we can see it's doing a better job for estimating this impulse response. So the point here is there's two things. So we have to choose the right kernel, and also we have to tune in those hyperparameter to have a maximum likelihood estimation. So now we're going to jump to estimation problem in reproduction kernel helper space, and now we're going to estimate the output Y as a function G. And here we need to use some high dimension space we're going to call the Hilbert space. And it's just a space that we have inner product, and also is complete. Every Cauchy sequence is converged. And if we use this regularization term as the norm of G square, maybe Euclidean norm, then it's called the Kernel regularization. So the space we like to use for those functions is we call the reproduction kernel helper space, and this space is helper space, and it's space of functions plus this condition that if we take this function Lx that defined from this helper space to R, and by taking any function U from this helper space, and the image is UEX is just evaluate the function U for X, and this should be continuous and linear functional and to be bounded. So here we have, if we take any function kx from this Hilbert space, then we can write this linear functional as ux, the evaluation of u at x value, and it's just the inner product of u and kx. So here we can define a reproduction kernel that's a function with two variables, kx z as inner product of kx and kz in this Hilbert space. So this theorem here of Moore-Arcson-Jean, this one is telling us that for in this space, this reproducing kernel hyperspace, is for each function there we can connect it to unique semi-definite kernel K. That's mean that this is a relation of 1-to-1, and that's good. And we see in machine learning for like when we do like classification, for example, and we to find the classifier to higher dimension, then instead of looking for the equation of that classifier, we need just the kernel, we just the inner product. So it's almost same idea. So here for this helper space, it's spanned with those representer, and it's separable space, and every function g of x evaluated in x is just linear combination of those representer at x. So some examples of kernels like Gaussian here, and this is the formula for Gaussian, and this d can be any distance, or we can use Euclidean distance. And those kernel Gaussian, it's good for approximation any functions that's square integrable. So another kernel here, linear. Linear. This is the way we can write the linear kernel, and this P is just matrix that's positive semi-definite, and if this P is satisfied, that is for rank, then we can generate linear functions from this kernel, and if we do that, then we can see that the estimation problem is going to become this way, and this is same like we did for regularized linear regression. So now if we take this linear and we add some constant kernel and then we multiply them together, then we can generate a polynomial kernel, and then we can generate the space of polynomial function with the degree d. So this is another kernel. It's called spline kernel, and this kernel is defined from 0, 1, 0, 1, and with this expression here, and this function g is given with this form. It's space-wise, and this is the graph of this spline kernel for value order k equal to 2. This is a 3D graph, and this is if we fixed x from 0 to 1, then we get those section graph. So represent theorem, this is very good to estimate this function, and the estimation of this function for this minimization problem here is just given with this combination of those representer. So it's just the sum of this coefficient Ci, and then here we just redo the kernel. So here this Ci, we can estimate this one from the data, and it's just k plus gamma in inverse y, and this k is just the gram. It's called gram matrix or the kernel matrix. And application of this is if we use a continuous time linear invariant system, and this is the system, the equation of the system. It's integration of inputs with impulse response. And the problem here, it's not like machine learning. This is a convolution between the impulse response with the inputs. So the goal is to be able to estimate this function here. So to do that, so we're gonna use it represent theorem, but instead of using the combination of those coefficient with the kernel, we're gonna do a convolution of the kernel, and that's what we have here. So convolution of the kernel, that's gonna give us with the combination with this coefficient Ci, they give us the estimation, and we can define this output kernel that is double integration for those two for this expression here. So the stable spline kernel is to define this stable spline kernel is we need to use this spline kernel. The spline kernel, as we did before, it was defined only from 0, 1, 0, 1. So we have to do some transformation for this variable s and t to make them fit in 0, 1. So we do some transformation, and then we apply this spline kernel. So this is the formula. And for k equal to 1 with this condition, then we get the TC kernel, that's special case. And then for k equal to 2, as we mentioned, is called the cubic stable spline kernel, and it's given with this form. So to include, we can see that that kernel has very good tools for system identification, especially for the challenge of bias and variance trade-off. And also, with the tuning the hyperparameter, we can get a better model. And this kernel doesn't work only for linear; can work on also for nonlinear. We just have to use the specific kernel that satisfies some properties of those impulse response. Thank you for your attention. Have a good day.